Today we're going to discuss about the relation between the equilibrium constants of different conditions. Okay, so the first one is what? Kp. So we have the equilibrium constants for different conditions where which are actually Kp, Kc, and Kx. Okay, so this is actually the equilibrium constants if we consider the pressure. Okay, or you can, if we can calculate the pressure of the reactants or the partial pressure of the all the components, actually the all the reactants and the products. And if you can calculate the composition or the concentration of the reactants and the products, then we can use this one Kc, and the final one is your Kx, where we used the mole fraction instead of the pressure. Okay, so let us derive the relations between these three form of equilibrium constants. Okay, so first one is the relation between Kp and Kx. Okay, so actually in your syllabus only we have to derive the relations for ideal gases. Okay, so ideal gases, so that means we are going to only deal with the ideal gases. Okay, ideal gases. So we have already know that Kp is equal to Kp is equal to uh, Kp is equal to P partial pressure of m to the power m partial pressure of n, that is the products. Now these are the products, and the partial pressure of a to the power a and partial pressure of b to the power b. Okay, this is for what? This is for a reaction, reversible reaction, which is your aa plus pb will going to react with each other, and they will going to form m mole of m and n mole of n. Okay, so for this reaction we have this equilibrium constants. Okay, if you can where pm is the partial pressure of the product m, and pn is the pn is the partial pressure of product n, and pa is the partial pressure of reactant a, and pb is the partial pressure of your this one is of the reactant b. Okay, so we have this actually we have already derived this relation. Okay, so now what we have to do, we have to derive a relation between this kp and this kp and first kx. Okay, so since we are talking about ideal gases, that means all the reactants, and we consider excuse me, that the reactants and all the products are ideal. Okay, and ideal gases actually. So that means they will going to follow, and in case of ideal gas we know that they will going to follow a law, a very well-known law, which is known as Dalton's law. Okay, so according to this law, the partial pressure of a component I is equal to the mole fraction of that component into the total pressure of the mixture. Okay, so if there are many gases are inside the chamber, then the partial pressure exerted by a component I is equal to what is this? This is your the mole fraction of that particular component multiplied by the total pressure of pressure exerted by the all gases inside the or on the wall of the chamber. Okay, so this is your partial pressure. Okay, so for this is your partial pressure. For this is actually the normal general condition. So this is I, that means this is the ith component. But here how many components are there? There are mainly 4 components are there: a, b, m and n. Okay, so the component a, so for this a, that is, this is a reactant, no? So reactant, we have what? Reactant. So reactant a, and also b is also your reactant. Okay, so for these two, let's suppose the partial pressure of this gas, let's suppose this is your uh, reaction vessel. Okay, in which the reaction is occurring. Okay, so there will be what? A will be there, b will be there, and after reaction between this a and b, they will going to form m and n. Okay, so yeah, but at equilibrium positions, all the components will be there. Okay, so that means all the reactants, a will be there, b will be there, m also be there, and n also be present in that vessel. That means that reaction vessel. Okay, so that the a will go, because all are what? Ideal gases, so they will going to exert some pressure on that wall of the vessel. So let's suppose the partial pressure exerted by the component a is pa. Okay, so and according to Dalton's law, how we can write? If the mole fraction of that component, which is a, is xa, that is, this is your mole fraction of a, then we can write this xa into multiplied by the capital V. Capital, let's suppose the total pressure exerted by all the components is capital P. So this is the partial pressure of what? The component A. Okay, so similarly we can write the partial pressure for B is equal to xbp, partial pressure of reactant M is equal to xmp, partial pressure of N is equal to xnp. Okay, so we have this relation, okay, of that means the partial pressure. We have we can calculate the partial pressure of each component by using the Dalton's law. Okay, so we have this value now. So what we can do, we can put the value or we can use this relation, or we can put the value of the pa, pb, pm and pn in this relation. So let us substitute this value, okay, in this. So it will be what? It will be kp is equal to, so pm is equal to what? Pm is equal to your x m to the power m, because this is to the power m, no? So we can write like this, xm. Okay, xm, because of pm is equal to what? Xm into capital P to the whole to the power what? M. Okay, hope you understand this point. And pn is equal to your xn capital P, total pressure, to the power n. Okay, and similarly in this case, x this is your a, and to the capital P to the power a, and here x b capital P to the power b. Okay, so this is your kp is equal to this one. Okay, so now we can simplify this one by using simple mathematics. Kp is equal to, because of p are we can write it like this. Okay, xm to the power m into xn to the power n, x a to the power a, x b to the power b. Okay, into p to the power what? P to the power your p to the power m, p to the power n, so m plus n. Okay, and here divided by p to the power a plus p, a plus p. Okay, so kp is equal to, and what is this? Actually this we know that kx is equal to x to the power m to the power m, x to the power n to the power n, x to the power it to the power a, x to the power b to the power. This is for what? This reaction. Okay, only this reaction. For this reaction we can write kx is equal to x to the power m xm to the power m xn to the power n. So this is your kx. Okay, so that means in place of this part, what we can write? We can write kx. Okay, because this is kx is equal to x m to the power n. So here the same thing, no? Okay, so we can write this one into here p to the power, actually what would be, it is your m plus n. Okay, and this is divided now, so minus k plus b. Okay, so kp is equal to kx p to the power m plus n minus a plus b. Okay, so what we can write here, kp is equal to kx p to the power, so here actually this is your what, the numbers of moles of the product, and these two are your numbers of moles of reactants. So that means this is your change of numbers of moles during that reaction. So del n represent one change in number of mole during the reaction. Okay, so del n represent change in, so this represent, okay, this represent change in number of moles during change in or change of, okay, during the reaction. Okay, so that means we have the relation, first relation. So first relation is what? So we have the relation between kp and kx, and it is actually kp is equal to kx into p to the power del n. Okay, so it is also, okay, so it is also shown in this notes. Okay, so you can go through it also. Hope after this you understand. Now let us discuss about the second relation, that is the relation between kp and kc. Okay, then finally we're going to relate the three of them. Now the second relation is actually, so we have to find a relation between kp and kc. Okay, for ideal gas equation, for actually ideal gas reactions. Okay, so the reaction should be for ideal gas, that means the reactants and products must be ideal gas. Okay, gases. Okay, so if they are a real gas, then it is not true. So this is your b, to find out the relation between kp and kc. So again, for ideal gas, again we have to consider that reversible reaction where a mole of a will going to react with b mole of b, and they will going to give m mole of m plus n mole of n. Okay, and for and the same conditions. Okay, all of the reactants and all of the products are what, in gaseous state, and they are we considered that they all follow the ideal gas equation, that means they are ideal gas. So we know that for ideal gas, for ideal gas pv is equal to nRT. Okay, pv is equal to nRT, but this is general, no? So for one component, so let's suppose vi. Okay, pi, and the partial pressure of ith component is equal to, because ni and RT, R is the constant, temperature is also your constants. Okay, and V is the total volume. That means this, let's suppose this is your reaction chamber. Okay, where the reactions will going to occur, and this is A and B will going to present there, and they will going to react, and they will going to form Mn, and after at equilibrium actually all of them are present. Okay, and here the partial pressure of component A will be what, according to the this ideal gas equation, it will be your PA is equal to and then let's suppose the total volume of this one is V. So PA is equal to your NA divided by V, because as we just what we can write this one, what PI is equal to NI V RT, same thing also. So NA V RT. T. Okay, similarly we can write for the others also. P is equal to and B by V RT. PM is equal to NM to divided by V RT. Pn is equal to N V by RT. Okay, and interestingly this one actually N I by V is equal to actually your composition, that concentration. Actually N by V is equal to concentration, so actually this is CIRT. Okay, so here what we can write, this is for CART, concentration of A present in that chamber and at equilibrium position. Okay, and here it will be your CBRT, concentration of B present at equilibrium, concentration of B at equilibrium condition, okay, and CMRT is equal to CNRT. So we have this value PA is equal to CART, PB is equal to CBRT, PM is equal to CMRT, PN is equal to CNRT. Okay, so we have this relation. So what we can do, we can substitute, or we can use this value and we can insert this value in this equation. Okay, so we have already this equation, m to the power m p n to the power n p a to the power, these are partial pressure. Okay, p a to the power a, p b to the power b. So this is actually small p. Okay, partial pressure. So here we have this value from that ideal case equation, so we can just put this value here. Okay, so let's insert this value. So it will be your CA PM, not PMRT. Okay, CART to the power your m. So this was not first one, this one CMRT. So CM, sorry, okay, this will be your CM, because PM na CM RT to the power m, CN RT to the power n, CA RT to the power a, CB RT to the power b. So we have this relationship. So now what we can do, we can take the CM CN to the power, this will be m, this will be your n. Okay, here CA to the power a, CB to the power b, but here it will be what, RT to the power m plus n, and this is your RT to the power a plus b, simple mathematics. Okay, so it will be your again we know that Kc is equal to actually Cm to the power m, Cn to the power n, Ca to the power a, and Cb to the power b. So this is actually your for this reaction. Okay, for this reaction we can write the equilibrium constant in terms of concentration like this. Okay, so that means Kc is equal to this one, that means this part same, no? So Kc, so this part what we can write Kc, and this will be what, RT to the power m plus n minus, in bracket, minus a plus b. So it is your K RT to the power del n, where del n is equal to the change of number of moles during that reaction. So it is your Kp. Okay, so that means we have the two relation, one is this one, another is the Kp is equal to K x p to the power del n. So that means Kp is equal to Kx p to the power del n. So okay, del n is equal to Kc RT to the power del n. So this is your relation, this is your relations. Okay, so it is very important, so try to understand this one. Okay, so coming to the so this is actually the relation between the three equilibrium constant. Okay, three form of equilibrium constant actually. Okay, so if you have any one, let's suppose we have this one, okay, Kx, then we can calculate Kp by knowing the pressure and del n. Del n can be easily calculated. I will going to show you, okay, how to calculate del n. So coming to the next slide. Okay, so now if del n is equal to 0, so what is the meaning of this? If del n is equal to 0, so let's suppose a reactions like this. A plus B will going to react to each other and they will going to form C plus D. Okay, so how many mole of A is present here? 1 mole, and this is 1 mole, 1 mole and 1 mole. Okay, so that means M plus N is equal to what? M plus N means this is M 1. Okay, so that means the number of mole of products. So M plus N represent what? Number of moles of product. Okay, so numbers of moles of product is equal to your 1 plus 1. 1 plus 1 is equal to 2. And similarly, the number of moles of reactant. Okay, so number of moles of reactants, how many moles are present? 1 plus 1 is equal to 2. So that means del n is equal to 1. That del n is the number of moles of product, okay, minus number of moles of reactant. Okay, this is the relations. Del n is equal to number of moles of product minus number of moles of reactant. So number of moles of products is 1 plus 1, that means is equal to 2, minus number of moles of reactant is equal to 1 plus 1 is equal to 2, that means 0. So if del n is equal to 0, let's suppose del n is equal to 0, then what will be happen? So we have that relation Kp is equal to K x p to the power del n is equal to K C RT to the power del n. Okay, so here it will be your Kx p to the power 0 is equal to Kc RT to the power 0. So it is Kp. Okay, so always remember that one point, anything to the power 0 is equal to always 1. That means x to the power 1 is 0 is equal to 1, y to the power 0 is equal to 1. Okay, anything you can write, anything, x plus y plus z divided by x square plus x cube plus y, anything. Okay, if it is to the power 0, that means always 1. Okay, so that means p to the power 0 is equal to 1. This is equal to 1, and RT to the power 0 is equal to also 1. That means we can write Kp is equal to Kx is equal to Kc. So if there will be no any change in numbers of moles during that reactions, or actually at equilibrium position, if there is no any change in the number of product and the number of reactant, then all the three forms of equilibrium constants are equal. Okay, Kp is equal to Kx is equal to Kc. Understand? So that is if it will be like, if the condition is like this, that means if it is 2 if the 2 mole of A will going to react with 2 mole of B and 2 mole of C will going to form and 2 mole of D, then also it will be 0. Okay, because the final net del n equal to 0. Okay, so I hope this you understand up to this one. So in your syllabus up to this actually is there in your chemical equilibrium chapter. So in the next class we will going to mainly discuss about chemical, not ionic equilibrium part. Okay, I mean ionic equilibrium. Hope you understand. Okay, so I will also add this PDF file in the description part of the YouTube video. Okay, so if you want to download, then you can download from there.